It is my pleasure to introduce the first plenary session speaker, Dr. Bill Siegle. For many years, it was my privilege to work in the development organization at AMD led by Dr. Siegle. It was a rare opportunity, as well as a challenge, to have a senior executive who had real expertise in lithography. Prior to joining AMD, Dr. Siegle had a 25-year career at IBM, where he became the director of the Advanced Technology Center in East Fishkill. He has served on the boards of directors of SRC and Semitech, and the public companies E-Tech, DuPont Photomasks, and currently ASM Lithography. Today, Dr. Siegle will share with us his perspective on lithography as it has evolved over the course of his distinguished career. Dr. Siegle.
Oh, yes. Glad Harry mentioned the background so I don't have to mention the disclaimers that go with the perspectives I'll be sharing with you today. In the interest of full disclosure these days, you always have to disclose where your biases come from. Well, good morning. It's a real honor for me to be able to address this group. This is an amazing conference every year, and I've enjoyed attending the last few years, although there's a little bit of mental overload by the end of the week. So I'm going to spare you some of that and give you a relatively simplistic high-level view of some of the observations I've made over the years and some of the lessons I've gleaned from those experiences. One of the problems with being an elder statesman in the industry is that your recollection of past events sometimes gets a little fuzzy. In fact, I have a friend who has had a serious problem with memory loss. His name is Fred, and he was sharing that with me, and I urged him to go see a doctor. So he went to his doctor, and he said, "Doctor, you've got to help me. I've got this terrible memory problem. I can't seem to remember things from one minute to the next." And the doctor looks at him and says, "Well, Fred, I'm sorry to hear that. Maybe I can help you. How long have you been dealing with this problem?" And Fred turns and says, "What problem?" So I don't think I'm that bad. But thanks to the internet and some good friends for recollecting some of the past aspects of this industry, some of the practices, and some of the things we've learned to do. This is a recollection that's probably one of my first images of lithography in the industry. Many of you won't recognize what this is, but this is a fellow cutting rubylith. Rubylith is a material that was used to cut out patterns that were going to be translated into masks. He would manually cut this, and then it would go in through a process that looks something like this. This contrast is a little weak here. You'll have to stretch your eyes a little bit. But that rubylith master would be reduced down in size to manageable proportions, and then would be moved to a step and repeat camera, where it would be reduced again and stepped and repeated on a chrome or emulsion plate. It would be inspected, repaired, and then that precious master, to protect it, would be copied to a submaster and then in turn to working plates. And those working plates is what went out on the fab lines to do the contact printing that characterized our early days. So in fact, this kind of 1X printing was the early workhorse of the industry. It was limiting, and the biggest limitation, of course, was defects. Because when you took a plate and you put it in rough contact with a wafer, it picked up dirt, it picked up particles, and it deteriorated quite rapidly. That's why you had that elaborate process for making many copies of those working plates. The advent of proximity printing, which allowed a small gap between mask and wafer, bought a little bit of time. But nevertheless, the 1X mask turned out to be a rather limiting issue. And in fact, lesson number one that I drew from these early years was, watch out for 1X masks. If your mask is the same feature size as what you're trying to produce on a wafer, you're always going to be limited by the perfection of that mask and your ability to keep it perfect. There was really a need to move to projection and reduction. That is, do what was done in the mask house. reduced down start with a magnified image, reduce it down to the wafer scale, and keep in projection, keep that master separate from the mask. It would seem like that was a straightforward thing to do because that was what the mask house done. Turned out that was not a particularly easy project, as some in the room, I was chatting with Bill Toby here this morning, and he can recall the early days of getting that technology to work. The reason it was hard is they had to have both speed and precision to get a viable production tool. One of my specific experiences at IBM was to work on a project called 5X LFS. IBM in those days, and this is early 70s now, made a lot of its own production equipment. The equipment industry had not yet matured to the level, anywhere near the level it is today, and so IBM built a lot of its own equipment. So it took a shot at building a step and repeat machine. They'd had some good experience with an automatic alignment scheme for proximity printers and thought that could be employed in conjunction with a stepping table to make a step and repeat tool. Well, it turned out that project was a dismal failure, and it ended up being scrapped with a lot of hardware that was in replication build being scrapped as well. And I looked at that at the time and I said, getting speed and precision from this thing is just never going to fly. This is never going to be a production technology. Turned out to be a bad general conclusion, but the specific conclusion for that project was correct because it was based on a bad assumption at the start. The idea was that a relatively crude stepping table with site-by-site automatic alignment would meet the needs of a production stepper. The fact of the matter was you couldn't do accuracy and speed on a site-by-site basis and get the job done. Other people would figure out that you can do good global alignment and fast, accurate stepping, and that's what eventually came to production. But the IBM project failed and led us to another important learning, in my opinion, and that is when your project gets in trouble, it's sometimes a good idea to go back and check the assumptions you started with, because often you'll find a flaw there that may account for a good source of the difficulties. Now, one of the things that helped IBM make the decision to scrap that project was that help came along in the way of Perkin-Elmer machine. This wasn't a total solution because, as I said, we wanted to be able to reduce and to project. But the Perkin-Elmer microline was a 1X scanner that brought projection. So it solved the problem of mask wear due to contact between mask and wafer, even though it retained a 1X form factor. It used a novel optical concept of reflection of mirrors to reflect the image through the mask onto the wafer, simple alignment system, and a relatively simple tool, as you saw in the earlier picture of Dave Markle, that sold like hotcakes during the 70s. This was a major revenue generator for Perkin-Elmer, and it really helped the industry make its next move along the line of higher integration levels with masks that in fact could last forever. Now, steppers were not to be denied and were eventually going to make it to production. And by the late 70s, a company called GCA managed to bring the first commercial step and repeat machine into production use. Now, this was not an easy machine to use, and I recall some war stories from some of my colleagues at IBM Burlington at the time who were trying to use this early machine on a production line. And they found they could predict the weather with it because each time the atmospheric pressure changed and a storm front coming in, this tool would drift. And that was just one of many little idiosyncrasies that had to be learned to make this a usable tool. But there were lots of people in the fray to develop this type of technology, and other companies would be showing up. Here you see that early GCA machine. It was a 10-to-1 reduction stepper, a Zeiss lens, mercury arc lamp source, precision laser-guided table, and it worked reasonably well for starters. But others came along, as I mentioned. And one of the surprises to at least the US industry was that Nikon and Canon showed up with very robust machines that in fact were well engineered to be usable production tools on a manufacturing floor. And those machines and their products would come to dominate the marketplace by the late 80s. One of the other little insights was that this was one of several outcomes partially attributable to the Japanese VLSI project that was run from roughly 76 to 80. And it was an example of government and industry working together, particularly industries that didn't necessarily cooperate very well with each other, but with the help of a little government urging, they did and produced some significant strides for Japanese industry. ASML also came into existence in this time period, not highly recognized in the 80s time frame, but it put a heavy emphasis on precision and throughput, priorities that would serve it well through the subsequent decades. Perkin-Elmer, who rode the 1X projection horse a little bit too long, lost significant amount of market share as the steppers matured and took over market volume. Eventually got merged into SVGL and even later into ASML, and did finally come to a step and repeat concept, but with a scan concept using step and scan, capitalizing further on the mirror concept. Now, the 80s brought us another significant change in the industry, and what I call the decade of cooperation. I think people took a look at what was accomplished with the VLSI project and said, we can do that too. And so there were a myriad of ventures that occurred over the 80s that created an infrastructure of cooperation in the industry. SRC was one of the first of those in about 1982. Now you have to remember, in the time frame of 1980, companies didn't cooperate with each other. There was a fear of antitrust challenges, and so rarely would you have two companies sit down and talk about what were common issues or challenges. SRC provided the first step of legitimacy for that, and it was a simple venture. Namely, semiconductor companies got together, pooled some funds to sponsor university research. Simple enough, but two very important results came out of that early cooperation venture. First of all, it did get the companies sitting down and talking about what are the common issues that we ought to fund some university research for. And secondly, it put silicon research back on the agenda of university research labs and produced students who were schooled in problems that were very pertinent to industry and were quick starters once they graduated and joined industry. Anyway, that positive experience set the stage for a more ambitious undertaking called Semitech 5 years later, which was a larger venture with initially significant government funding as well to support manufacturing technology. In parallel in this time frame, the Department of Defense had a program called VISIC, Very High-Speed Integrated Circuits, aimed at making sure the government had access to leading-edge technology for national security-sensitive applications. In Europe, you have IMEC and LETI that were engaged. Late in the decade, IBM joined a development alliance with other companies to collaborate on the expensive development of next-generation technology. And the Center for Nanoscale Science and Engineering at the University of Albany became a robust entity that it is today. So I say lesson number 3 from this time period was the testimony that said sharing enables faster progress. And I think very much that the infrastructure that was of cooperation that was created during the 80s set the stage for and enabled an impressive rate of progress that would occur in the decade of the 90s. And in fact, the 90s saw huge strides in integration levels. I remember, and I'll recount this a little later, but I remember giving a talk in the year 2000 to a group of SRC graduate students. And I said to this group, if you had told me in 1990 we would be manufacturing in the year 2000, I would not have believed you, because the advances over that 10-year period of time were that dramatic. And in fact, in lithography, we saw a progression of wavelengths from I-line 365 to deep UV 248 and then 193 over that same time period. But there was a problem. This didn't just happen. There were several obstacles for this to occur. And one of which, you can't read this, but it's a copy of the patent issued to chemically amplified resist. Grant Wilson, Hiroshi Ito and team who invented this sort of breakthrough concept that would unblock the resist element of moving to shorter wavelengths. So chemically amplified resists and also the intense light sources of excimer lasers is what enabled that move finally to occur to shorter wavelengths. If you looked at that patent, you'd see that that patent was filed in '82 and issued in '85, but it would be almost a decade before that would see wide-scale production use. Part of the reason for that is another example of sharing. IBM was the owner of that patent and had further evolved that concept into a robust, fab-robust resist technology called Apex. But IBM declared that a trade secret at the time, and so it was tightly bottled up in IBM. But with IBM engaged in joint development with a number of other semiconductor companies, and the equipment industry not willing to ramp up production of deep UV systems until there was a market that would be enabled by a decent resist technology, IBM finally agreed to make that piece of technology available, and by the mid-90s then it did become widely available, and the subsequent reduction of wavelengths that we saw was able to occur. So it's another example of how sharing, in this case a specific example of sharing, enabled some significant progress to occur. Now, over this period of the 80s and 90s, there's also, and continuing today, lots of work on alternatives to conventional optics. Bill Arnold has a wonderful chart that I thought I might use, but it's too complicated to talk to, that shows a tree of the evolution, the straight line evolution that we're talking about here, plus all the side paths that have been evaluated and explored over time. We ought to ask him to give a talk sometime just on that particular development tree. One of the other opportunities or possibilities, if you will, is E-beam lithography. After all, it's played a major role in mask making, and just like optics moved from the mask shop to the production floor, one would think E-beams could move from the mask shop to the production floor. And in fact, there was some limited success at IBM in direct write in manufacturing. I see Hans Pfeiffer here, whose team in East Fishkill developed a variable shaped spot version of an E-beam technology that in fact was successfully used to write multiple part numbers in an IBM environment that happened to need that application at that point in time. IBM was building its mainframes out of relatively low integration level bipolar gate arrays, and so there were lots of part numbers needed to build a mainframe processor. Not only were there lots of part numbers, but because of the relatively immature state of logic simulation, they got changed frequently as a machine was being debugged and as improvements were made on it. And so there was a huge churn of part numbers. So the ability of a modest but satisfactory throughput E-beam machine to direct write those personalization levels enabled IBM to churn out hundreds of part numbers, as many as 10 part numbers on a wafer, in an entirely paperless system that was sort of a modern hallmark of direct write E-beam in production. Turned out to be a narrow window in time because as resolutions further reduced, the part number counts went down, the throughput of the E-beam tools went down, simulation tools improved so there wasn't as much churn of the designs, and so this then ceased to be a workable methodology going on into future generations. But it was a single point in time where direct E-beam was used in production. The fundamental issue, of course, is that there's a basic trade-off between resolution and throughput that limits what you can do with an E-beam. As you call for smaller and smaller feature size, throughputs tend to go down in a square law relationship, and you're very quickly down into minuscule throughput rates. That's led, of course, to discussions about massively parallel systems, which enjoys a lot of attention at this conference every year, and I see some excellent presentations this week also on various of the proposals for massively parallel E-beam systems. You'll hear and can hear about at least 3 different formulations of massively parallel systems that are being considered. I won't try to describe them here. It would take a whole talk in itself to go through these. But it's an active subject still of research and development. But I glean lesson 4 from this example, and that is it can be tough to beat the laws of physics. It's a fairly fundamental issue we struggle with in electron beams, and I think that's part of what we're dealing with. Now, there's another also ran that occurred during this time frame that IBM had a major role in, and that was X-ray lithography. The thought here was to make a massive stroke in wavelength reduction down to roughly the nanometer level using hard X-rays. IBM Research Division pioneered some work here using a light source at the Brookhaven National Laboratory, synchrotron light source, with fabrication at the Watson Research Center, and actually built a successful 4-layer device demonstration, which in turn led to a full-blown development project in East Fishkill to develop a compact synchrotron source, compact by using superconducting magnets, and to attempt to develop a practical lithography system for that function. It was based on the assumption that when we get much below a quarter micron, optics would run out of steam and we would need something like X-rays. Little detail, it required a 1X membrane mask. So those of you who remember some of the earlier lessons might think that there's a problem coming here. Nevertheless, this was a major project. There was an issue of the IBM Journal of Research and Development about, I think, 1993 that detailed in great detail all the elements of this particular development project. The cover of that magazine had an illustration that showed what a deployment would look like. At the center of that illustration, you see the compact source, massive shielding around it, and then a set of beam lines scattered around the outside to, I think, about 10 beam lines could be distributed around a particular source. Compact source was actually delivered, looks like a steam engine here, but that was delivered to the development center in East Fishkill and became a fully functional development capability. However, the project was abandoned in the early 90s as it became clear that optics was going to blow right through the quarter micron limit, and in fact that the technology would not be needed for that level of application. If it had been continued to be pursued at finer and finer resolutions, you can well imagine that that 1X mask would again have been a limitation in the manageability and the workability of that technology. Now, we said that you can't violate the laws of physics, but it turns out that there is quite a few things you can do to trick Mother Nature a little bit. And one of the other things that occurred over the 90s was a variety of tricks to correct for optical distortions that became increasingly dominant as resolutions approached the wavelength of the light being used. Things like scattering bars, phase shift mask, optical proximity correction, playing with illumination, the aperture for illumination sources, tweaking the projection lens itself. All these things became things that people began to manipulate to optimize the printing process. ASML in particular put together the efforts of a company called Mask Tools and Breon, as well as enhancement in the stepper, to create what it likes to call holistic lithography. You'll hear bits and pieces of talks this week about elements of this, but it's basically a two-pronged attack on the problem of improving the optical result that you get. One prong consists of doing all the things you can think of to tweak up the mask with some computationally intensive tricks like proximity correction, like taking into account the characteristics of the illumination source and the characteristics of the stepper itself. And then when you've done everything you can there to optimize the mask image, you do another set of things post-exposure to measure your result and feedback corrections to tighten the control that you can get of the printing process. It's an elaborate process with many sub-tools involved, but it can make have a significant effect on the quality of the end result that you print. So I'll repeat my lesson 4 here, that it's tough to beat the laws of physics, but if you use those same laws of physics as clever as you know how, you can sometimes come pretty close. Nano-imprints, another possibility that's getting a lot of attention in the last several years of this conference. And this is a clever technology wherein you use a 1x template to emboss images on a wafer. Produces remarkable image fidelity and busts free of the RLS triangle of constraints that the resist developers struggle with. The trade-offs between resolution, line edge roughness, and sensitivity that seem to be a sort of a Gordian knot of constraints that you can't fix one without compromising the other. This technology bypasses that issue. Unfortunately, because it again makes use of a 1x mold here, you recreate the master submaster working template methodology of 1x contact printing, and defectivity is again a major concern that people struggle with to make this a viable technology. There are some specialized applications for which this might be very suitable. There's been work over the last couple of years in bit patterned media for hard disks that is tolerant of defects and less demanding of alignment, for which this might be a good possibility. Here's a particular set of images from a Semitech project to characterize some of the characteristics of this technology, and it indeed produces very impressive imaging that I think is remarkable when you consider the way it's being produced. So with nano-imprint, again, I would remind us that the 1x mask is potentially a limiting factor here in the applicability of this technology. So we come to EUV. EUV is really another X-ray technology, but an order of magnitude longer wavelength than the hard X-rays that IBM worked on. It's 13.5 nanometer soft X-rays, and the technology was called EUV to separate it from the, at the time, stigma associated with the hard X-ray project. With these longer wavelength X-rays, you can shape the beam with reflective mirrors and reopen the door of reduction printing. It again gives you a big step in wavelength reduction, but without the limitation of 1x printing that characterized the older X-ray technology. It takes large, fairly expensive tools to do this job, but the biggest potential here, of course, is that it provides and offers an opportunity as a simplification for multiple patterning. And in fact, it will be interesting here, the successful implementation of this technology will be based more on cost justification than on image size reduction. And the cost justification will come from the reduction associated with limiting multiple patterning. Multiple patterning brings enormous complexity to the wafer process, the mask process, and in particularly additional processing steps beyond just multiple masking. And so the cost offset that can be gained by single level printing again is substantial and will be the means whereby people switch to this technology. Pilot systems are available today for this, to practice EUV, but we still need advances in, most notably, source power to get throughput up. And source power has to get to at least 100 watt level, ideally 250 watts, to get up to throughput levels that the industry is now accustomed to. In addition, of course, we need production-worthy masks, resist, and metrology, all of which exist at levels sufficient to support piloting activity going on today, but which are probably not yet ready for full production-worthy deployment. This relatively simple chart gives you a vivid illustration of the leverage associated with the wavelength reduction. The top of this graph shows a simple pattern printed with a 1.35 NA 193 immersion stepper, and below it is that same image printed on the current pilot systems, the 0.25 NA 13.5 nanometer system. Remarkable improvement in image clarity, and it's not hard to see how this could in fact obviate the need for multiple patterning in a particular situation. The system is from a distance perhaps looks a bit like a conventional stepper, but it is a large system. The source itself is pretty cumbersome. And its most significant features are a reflective 4x reduction reticle, a 6-mirror projection lens, a vacuum environment, of course, the whole system has to operate in vacuum, and the 13.5 nanometer light source. The system that ASML intends to be a production system is the NXE 3300, has a higher NA, 0.33 NA, and is currently in integration testing in Veldhoven as we speak. This is a pretty fresh set of images from that, which show the step in resolution that's available with the increase in NA. But this tool has also been able to demonstrate satisfactory overlay in a mix and match mode with 193 immersion. See some data here on the right that shows 3-ish nanometer overlay in this mixed mode. So you might ask the question, well, when is this guy going to make it to production? And this gets to the question of predicting the future. And I've learned over the years that predicting the future is hazardous business. And I came across an entertaining chart in my research here that I thought I'd share. Semitech used to run a NGL, Next Generation Lithography workshop. And here's a slide from a 2001 version of that workshop. Now, one of the practices in that workshop was to ask people to predict when the next future generations of technology would be deployed. And these are experts from a whole bunch of companies, so this is not just men on the street kind of opinions. So there were 18 people in this survey, and at that point in 2001, they unanimously predicted 193 nanometer would do the 90 nanometer job. But if you look over to the right, 45 nanometer and 32 nanometer, nobody had 193 nanometer being deployed in that time frame. 2/3 had EUV in production, and the rest of them a variety of e-beam applications. So even the experts of our industry were woefully off the mark here in terms of predicting what would happen when at which point in time. So lesson number 6, my final lesson here, is that it's impossible to predict 10 years ahead. A couple, 3 years we can actually do pretty well. But beyond that, and particularly in the lithography business, there's always a surprise lurking around the corner. Who knows? We may see, and I'm sorry I didn't cover it in the talk itself, but I think one of the exciting new things on the table in the last few years is directed self-assembly. And what role that will play in simplifying multiple patterning, for example, is yet to be seen and could be one of the surprises of the next decade. So I'd like to recap at this point the lessons that we've shared. Watch out for the 1x masks. When in trouble, go back and check assumptions that you started with. Cooperation is enormously helpful to speed the rate of progress. Don't underestimate the extendability of established technology. It's tough to beat the laws of physics, but actually you can come close sometimes if you're tricky enough. And you can't predict 10 years ahead. I'd like to thank a number of people for help in putting the presentation together. Bill Arnold with discussions and illustrations. I borrowed some illustrations from prior presentations by John Bruning and Chris Mack. John Warleman dug up some of the X-ray pictures for me. Semitech presentations were also very helpful. But I think especially I would acknowledge the thousands of lithographers who are here today and every year, who in fact make the progress in this industry happen. So with that, I'd like to thank you for your attention and